Okay, so today what I want to talk about is Grover's algorithm. And I've mentioned a little bit what this does, but let me be more formal. So Grover's algorithm is a quantum algorithm for an oracle problem. The oracle problem is sometimes known as database search. People seem to find that name a little confusing. Maybe a better name is unstructured search. And so here's what this problem is. So we have an oracle. And the oracle maps, there's n, big N possible inputs and 2 possible outputs, 0 and 1. And we want to find if there exists an input x0 such that O of x0 equals 1. OK, pretty straightforward. Your goal is to see if this oracle always gives the output 0, or if sometimes it gives 1. And the thing is that if there's just one input, x0, that has output 1, then clearly, clearly it's going to be very hard to find. It's going to be hard classically or quantumly. And classically, the clear intuition is that you basically, because this is an oracle, you have no ability to look inside. There's no structure here. It could just be any entry x0 that happens to be 1. And so you can't really do anything much better than trying things exhaustively, right? So classically, this takes omega of n queries. And so I guess I mentioned this omega notation. So it's like big O notation. Big O says less than or equal to this function. In this case, it's greater than or equal to that function. But obviously, it's also less than or equal to n, because you can just try every input. And so what that gives you is this theta notation, capital theta, which means that it's exactly, it's both omega and of n and big O of n. So asymptotically, it's exactly some constant times n. So the reason this is an interesting problem, as I said, it's a kind of a proxy for any kind of search, right? Obviously, the case where you really have some black box is an unrealistic one. It's an idealized one. But for instance, suppose you want to solve an NP-complete problem, like satisfiability. Well, one way you could try to do that is to go through all the possible witnesses for this problem. So in the case of satisfiability, that means assigning the variables to some values, OK? And then evaluate your checking function on that witness, right? So in the case of satisfiability, you take your possible assignment of variables and evaluate the Boolean formula. And if the Boolean formula is true, then you've succeeded. You found a witness. You know that the formula is satisfiable. And that corresponds to trying the input x0 here in this oracle and getting the output 1. And if you try the assignment and it's 0, if it's false, then you have to try again. And so the checking function there is an actual implementation of some particular example of this oracle. Yeah.
So the Zn, n is x, n just counts the total number of inputs I have, right?
Yeah. Yeah. Total. Yeah, the total possible range of inputs.
It's just the labels for the different.
Yeah, it's just the interval, say, from 1 to n is the possible inputs. Or 0 to n minus 1 would be more computer science-y, but yeah. OK. And so then this problem can, because you can use it for an NP-complete problem, you can use it for any problem in NP. But more generally, just for a wide variety of searches. OK. And so let's see. Another example is suppose you have some cryptographic system, obviously if it's RSA, you're better off using Shor's algorithm if you can. But if it's some other crypto system where we don't know how to break it by quantum computer, you might say, as the eavesdropper, I want to break this. How do I do that? Well, there's some long list of possible keys. And so I'll just try all the keys. And one of them is going to be the correct key. And so I can if I happen to figure out the correct key, then I can break the system. Okay? And you can sometimes take advantage of structure of the system to speed that up. But if not, then you're trying this exhaustively long list of keys, and it's going to take a really long time. And then so a faster quantum algorithm to do this will speed that up. And so the practical upshot of knowing that quantum computers can speed up these things is that even if we don't have any other kind of quantum algorithm to attack this particular crypto system, you should probably increase the key size just to take account of this exhaustive speed up of exhaustive attack. Yeah, and so there's a variety of other ways you can use this type of algorithm, and in the homework, actually, you're going to explore a couple more, okay, to give you kind of an idea of the range of things you can do. So it's really a very useful algorithm. But the quantum algorithm doesn't give an exponential speedup, as I said yesterday. It just gives a polynomial speedup. So why is that, and what does it actually achieve? So what Grover's algorithm does is, instead of using O of n queries, state of n queries, it uses about square root of n queries. And we'll make that more precise as I describe the algorithm in detail. And this is, I should say, there's also a lower bound that you can prove quantumly, which is for this oracle problem. And because it's an oracle problem, we can prove lower bounds on the queries. And the lower bound is that it takes omega of square root of n. So it turns out that Grover's algorithm actually is the kind of the optimal quantum algorithm for this problem. And so the intuition of why this is, well, suppose classically we're just trying random inputs to see if we can find one. And basically, that's the best you can do. I mean, eventually, you'll start to repeat things, and that's obviously you should avoid that. But that's kind of a lower order effect, right? And if you try randomly, well, each time you try it, there's a probability 1 over n of getting the right one. And so if you try about roughly n of them, then eventually the odds are pretty good of getting the right one. Now, quantumly, well, we can do something more than probabilities. We can do coherent amplitudes, right? And so if we just kind of superposition of all things, of all possible inputs, well, if we just measure which one we have, that's a probability 1 over n again. But before we measure, there's an amplitude in that superposition 1 over square root of n, because of Born's rule, of the right input. And Grover's algorithm then is a way of getting those 1 over square root of n's of the right input to add up coherently. And so you can get that amplitude to add up coherently with only about square root of n queries. Okay. Now, it's not at all obvious how to do that. And this is where the actual algorithm comes in. But that's the intuition as to why you can get this square root speedup. OK? OK. So how does the algorithm actually work? So what I'm going to do first is I'm going to specialize to the case where I know that there's at most one marked element. So this x0 is sometimes called a marked element. And so I'm going to try to solve the algorithm in that case. So what we're going to do is we're going to do something that, obviously it's going to have to treat the marked element differently from the unmarked elements. But it's going to behave symmetrically on all of the unmarked elements. Okay? So therefore, we can work in a two-dimensional Hilbert space spanned by S and T. And so S is the basis state indexed by x0, the marked element, and T is the superposition of all of the other basis states. Okay? And I mean, we're going to go in and out of this Hilbert space, but basically we can analyze our algorithm only by looking at states that are superpositions of S and T. So of course, we don't actually know what S is at this point, or we're trying to figure that out. But it's still going to be just the way we happen to do things will live within this Hilbert space. So let me draw a picture here. A little bit bigger. So this is S, and this is T. So that's the two-dimensional Hilbert space we're working in. And at some intermediate point in the algorithm, we have some state psi here. And I'm going to write psi is equal to alpha S plus beta T. OK, so what can I do? What kind of operations do I have available to me? Well, one thing is we can apply the oracle. And of course, the standard way of applying this oracle, which is a classical, quantum version of a classical oracle, involves adding in an ancilla. But using this phase kickback trick that I hope you developed in the tutorial on Tuesday, I can just do one query, and I can do a phase of -1 when the oracles gives the output 1, and a phase of +1 when the oracle output is 1. So let me call that operation -1 to the O. And so then -1 to the O side, well, S is the marked element, where the oracle gets output 1. So I'm going to give a phase of minus there. And then T is the superposition of all the unmarked elements. So they keep the phase +1. Okay, so in this picture of our two-dimensional Hilbert space, this state psi goes, the T component stays the same, and the S component gets reflected. So this here is -1 to the O psi. OK, so what else can we do? Well, that's kind of all we can do with the oracle by itself. But we can do other things that don't involve the oracle, right? Just involve regular gates. So for instance, we can take the state all zeros and do the Hadamard transform on it. That gives a superposition over all inputs. So let's call that U. And U, the superposition over all possible inputs, is S plus T. So it actually is in this Hilbert space. OK? So we can stick it in here. Maybe I should use some colors. So this will be the state U. And it's going to have an angle theta with T, which will be important later. OK, So that's one thing. But that's just making a state, right? That's not something we can kind of continually do to alter things. So let's see, what else? So we have this one reflection where psi goes reflected over the t-axis. Can we do another reflection? The answer is yes, we can, right? So, for instance, we know how to reflect over the state all zeros. We can say the all zeros state goes to itself, and everything else gets a minus sign. So let's call that operation f sub 0. So f sub 0 of all zeros equals all zeros. And f sub 0 of, maybe call it y, is equal to minus y when y is not equal to all zeros. OK? Now, this thing, of course, is not an operation in this two-dimensional Hilbert space, right? Because it's treating the all zeros state differently from everything else. Whereas, unless x0 happens to be all zeros, that's not this Hilbert space. But remember, we already know a relationship between all zeros and something that's in that Hilbert space. So what if we do the Hadamard transform on this f0 and do this in the Hadamard basis? So let's call this operation minus 1 to the u. So what does this do? Well, if we have the state u, it'll map it back to all zeros. And then it gets of sign plus 1. And then we map it back to u. OK? So minus 1 to the u is equal to u. And if it's minus 1 to the u times something that's orthogonal to u, well, then the Hadamard transform will map it to something that's a superposition of anything but all zeros. Sorry, yeah, anything but all zeros. And then it'll get a global phase of minus 1 for it. And then we map it back to this thing it started with. So this will be minus of its state. So this thing here is a reflection over u, in just the same sense that the oracle call was a reflection over t. OK? So if we write our state psi in terms of u plus something orthogonal, the orthogonal part gets reflected, and so we have the same component along u, and OK, it's getting a little crowded here. And we have in here, maybe I should do this one in blue. Have in here the state minus 1 to the u psi. OK? So what does this do? So the state u had an angle theta with t. Suppose the state psi has an angle phi with t. So what are these angles after these operations? Well, the state down here, this angle here is going to be phi as well. And yeah, OK, so sorry, I guess I just didn't want to draw this. That's why the thing is too crowded. OK, so what I actually want to do is not apply this minus 1 to the u directly to psi. What I want to do is I first want to apply this thing, and then apply minus 1 to the u. And then you'll see what happens. OK, let me do it over here. here. OK, I know what I can do. I can do this here. So, so this is kind of sideline. So we have -1 to u. And then we have this operation g, which is going to be applying -1 to the o and then -1 to the u. And so what does that do? So it takes psi, reflects it down to this thing down here. So we have the angle phi down here. And then we reflect it over u. And now the angle is phi plus theta. So we're going to get an angle phi plus theta up here relative to u, which is phi plus 2 theta relative to t. And this is g psi up here. OK, so that was the upshot, is that the angle phi under g goes to the angle phi plus 2 theta. Sorry, I know I presented that in a slightly disorganized way, but did everyone follow the argument in the end? Just, we have the state psi, we apply -1 to the o. So instead of an angle phi plus phi, we have an angle minus phi. And then we reflect over u with -1 to the u. And then, so this angle phi plus theta becomes phi plus theta from u, which is phi plus 2 theta from t. OK, so what we've done with this g operation is we've taken this psi and we've rotated it by 2 theta in that direction. OK, and that's a good thing, because we're rotating it, well, the way I've drawn the picture, we're rotating it closer to S. OK, in particular, if we start out in this region, where it's kind of mostly T and a little bit S, then we are getting closer to S. OK, so so what's the algorithm? This is Grover's algorithm, in its simplest form anyway. So first of all, we're going to start with the states u. And I'm going to call this psi 0, because it's the first step of the algorithm. And we do that by doing the Hadamard on the all zero state. And then the next step is we're going to apply this g operation m times. Big M times, where big M has yet to be specified. And then the last step is measure to get a candidate for x0. And finally, so up to here has been the quantum part, and then here is just a straightforward classical part. Use the classical oracle. To check O of x0. Repeat if it's not 1. OK, and the reason we need to do that is because after step 3, if we've chosen M well, the probability of getting a marked element is high, but it might not be exactly 1. OK, so once we get this x0, we measure, we get some x0, which we hope is a marked element, but we should check if that really is. OK, and so how many oracle calls does this use? Well, each time we apply g, we're using the oracle once. And then we use it 1 down here. So this is m plus 1 queries. OK? So now why does this work? Well, so at this point, we're starting out with an angle phi 0 between t and the state psi. And that's an angle theta. And then this one, well, we step through states psi I. So I guess I've been calling them psi k, each of which is what we get from applying g one more time. And the angle between psi k and t is theta plus 2 times the number we've called the oracle. A number of applications. Sorry. OK, so each phi k is phi k minus 1 plus 2 theta. And so what that means is the total angle started as theta, and we've added 2 theta k times. So it's 2k plus 1 theta. That's what I wanted to write. OK? And so the state psi k is therefore equal to cosine phi k t plus sine phi k s, which is cosine 2k plus 1 theta t plus sine 2k plus 1 theta s. OK? Does everyone follow this part? Yeah.
What is your t you're choosing here? Is it?
The t is the t over there. OK? So I don't know what t is. I don't know what s is in particular. But this algorithm doesn't, this is what I'm actually doing. And it makes no explicit reference to s and t. It's just I know that we happen to start at an angle theta away from s and t in that 2-dimensional Hilbert space, whatever that Hilbert space might happen to be. And that I'm rotating in that Hilbert space, whatever it might happen to be. And this is the state I get at any given time. Any other questions? OK, so clearly what's happening here is that we're starting here at u, and then we're rotating and rotating and rotating until we get to s, or somewhere close to s. Of course, if we continue to do it, we would rotate further and further away from s, right? And then if we kept on doing it, we get back to t, and then we get back to s again, and back to t, and so on. So we want to stop after the right number of times. We can't just say, oh, let's let m be really, really large. We have to let it be the right amount. And so what's the right amount? So what we want is that 2m plus 1 times theta should be about pi over 2. Right? Then we've rotated all the way to s, or very close to it. So obviously we want m to be about pi over 4 times 1 over theta. We're working with big enough systems that the plus 1 here is negligible. Okay? So in order to figure this out in terms of real parameters in the system, we have to figure out what theta is. So what's theta? Well, we can figure it out by taking the inner product between u and t here. But I have to be a little careful because now my habit of not normalizing stuff will mess me up if I try to do that. So what are the normalized versions? Well, normalize U, U is the superposition over all possible inputs, right? And there's big N of them. So I should really have 1 over root n times U. And the normalized T is, now it's the superposition of everything but x0. So it's n minus 1 possible things. So 1 over root n minus 1. And then cosine of theta is the inner product of these two things. And what's the inner product of u and t, the unnormalized versions? Well, we get one added term here every time they're the same. And t is a superposition of everything but x0. U is a superposition of everything. So we get one term for everything but x0. So there's n minus 1 such things. So this is the square root of n minus 1 over n. Which also means, of course, that sine theta is square root of 1 minus this squared is 1 over square root of n. And when n is very big, sine theta is about theta. So we're saying that theta is about 1 over square root of n. OK? And so plugging that back in up here, we find that this is pi over 4 times the square root of n. That's about how many queries we should do, how many iterations of Grover's algorithm we should do before stopping. And when we do that, the state will be very close to the marked element x0. OK? So are there any questions on that? This is all of Grover's algorithm for a single marked element. Yeah?
What happens if you have 2 marked elements?
That's the next thing. So, but are there questions on the 1 marked element case? Yeah?
How does the element of what you were saying in the beginning about the coherence kind of factor in here?
Yeah, so because I'm doing a rotation in this 2-dimensional Hilbert space, that's a coherent thing, right? And so every time I do that rotation, I'm getting this angle 2 theta. I'm kind of getting closer to s by this angle 2 theta, which is that 2 theta is about 1 over root n, so it's about 2 over square root of n. And so that's kind of where the amplitude is accumulating coherently. Yeah, I mean, it's hard to make very explicit contact between this intuition of adding up the amplitudes and doing this rotation. But that's what adding up amplitudes means. It means doing some rotation in the same direction in a Hilbert space. Any other questions? OK, so yeah, so what happens? What happens if there's multiple marked elements? So now suppose we know that there's exactly t marked elements. So we're going to apply exactly the same algorithm, but big M is going to be different. And so, OK, maybe I shouldn't have put this all the way up there. So for t-marked elements, now we're going to let for the analysis, we're going to let S be the sum over all x, such that O of x is equal to 1. So that seems like the right generalization of the S we had before, instead of just being one marked element. So again, the idea is we're going to treat all the marked elements symmetrically and all the unmarked elements symmetrically. So this is a superposition over all the marked elements. And then T is going to be a superposition over all the unmarked elements. And U is still S plus T, which is still the superposition over all X. OK? And so once you do that, well, we still can do this minus 1 to the U operation. That's exactly the same. That didn't involve the oracle at all. And this minus 1 to the O still does this. Right? It still takes the superposition over marked elements to minus themselves and the superposition over unmarked elements to plus themselves. OK? So minus 1 to the O and minus 1 to the U are the same. G is the same. It has the same picture applies. The only thing that's different now is this angle theta is different. So what's the angle theta? Well, so now the normalized now I do need to push that back up. So now the normalized U is still 1 over root NU, but the normalized T is now so this is now a superposition of n minus T things. So this is a 1 over root n minus T times that. And so cos theta is 1 over root n minus T times ut. And T is only a superposition of n minus T things. So this is a factor of n minus T. And so we get root n minus T over n. And sine theta is then root T over n. OK? So everything else is the same. So if T is really, really big, like comparable to n, then the next approximation breaks down. But in the normal case, where T is much smaller than n, this is, again, about theta. And therefore, we want to pick m. Well, we're still picking it to be about pi over 4 times 1 over theta. But now that's pi over 4 root n over t. OK? So here's one thing where you can see where the quantum algorithm is somehow not gaining as much as the classical algorithm. Right? So if we had classically, we had t marked elements. Every time we tried something, instead of a probability, tried something at random, instead of a probability 1 over n of getting a marked element, we get t over n. Right? And so the whole algorithm would be sped up by a factor of t. In the quantum case, it's sped up by only a factor of square root of t. OK? But that's kind of the price you pay for speeding up by a factor of square root of n, which is certainly bigger. Yeah?
So do we know a priori how many marked elements there are?
Well, so far, I've been assuming that we do know.
But aren't we just trying to test if there exist any at all? Like, isn't that the goal?
Yeah. So the real goal is indeed, we don't know how many elements there are. Well, it depends on the system. You might know, you might not know. But certainly, there's many cases where you don't know how many marked elements there are. And that's a problem, right? Because if there's one marked element, you want to run for time pi over 4 square root of n. But if there's 4 marked elements, then you want to run for half that time. And if you run for a time pi over 4 square root of n, you'll get back to where you started. Well, maybe minus t, roughly. And you don't want to do that, right? So you really have to know how long you can run this. Otherwise, you won't get a good answer. Or you won't get an answer with high probability.
So does that mean that this isn't very good at solving the problem as written there, which is just to see if there exists?
It is. I just haven't told you how yet.
Sorry.
I just have not told you how to deal with that problem yet. OK, so there's actually a couple of different modifications you can make that will let you solve the problem when you don't know how many marked elements there are. And that's the next thing I'm going to do. But I just want to make sure people understand what I've done so far first. So are there any more questions on the case where we know how many marked elements there are? Okay, so yeah, so what if we don't know? Oh, great. There we go. Okay. Okay, so note that we don't need to know, when t is relatively large, we don't need to know the exact number of marked elements. We just need to get approximately right? If the probability of success is 2/3 rather than 99%, well, okay, that'll, we can try it a couple of times and eventually we'll get one with very high probability. But we do need to kind of know roughly how many marked elements there are. So let me try to present it this way. So suppose we don't know what m we should pick. Sorry. We don't know what m we should pick. So this is the m axis. And here we have the probability of success. So certainly it starts at 0. So this is 1. That's the best we can possibly get. And as we do more and more iterations, the probability increases and increases all the way up to 1 or very close to 1. And then it decreases again as a cosine. So it's going to look something like this. I guess cosine squared, since it's a probability, or sine squared. And moreover, we know what, I mean, if we knew the number of marked elements, we would know what the period here was. So so this first peak here happens at pi over 4 root n over t, roughly. Right, and this next peak at 3 pi over 4 root n over t. Okay. So in order to find, roughly speaking, what t is, we'd like to know this distance here, the distance between peaks. So in other words, what we have, if we look at the probability of finding a marked element, is we have a periodic function, and we'd like to know what its period is. Luckily, we have a quantum algorithm that does that, Shor's algorithm, right? So that's what we're going to do. Is we're gonna run Grover's algorithm for k iterations, where k is a superposition. So in particular, we're going to do sum of k, and then we're going to do the Fourier transform to determine t. And then once we've done that, we know roughly the number of elements, and we can just do Grover's algorithm for the appropriate number of iterations to find the answer. So what does this look like? So we have So these ones here are going to be our kind of a Grover. And these ones here are going to be our kind of our Shor register. And the idea is we're going to run Grover's algorithm on this register k times, where k is given by the value in this Shor register. And then we do the Fourier transform. And measure here to find the period. OK? So, so this variant of Grover's algorithm is actually a counting algorithm, right? It's an algorithm that gives us approximate counting of the number of solutions. And actually, if you really just want to solve that oracle problem directly, which is there an input, a marked element or not, this is already enough to tell you that, right? Because if it's not marked, then the period will be, well, kind of, in some sense, 0, or in some sense, infinite, right? It's just going to be flat 0. You're never going to get peaks. If you get pi over 4 times square root of n over something, then you know that there are marked elements. Right? An approximate counting of the number of marked elements will tell you. I guess if it's really one marked element, no, if you do this well enough, that will give you the answer. Okay. And anyway, so if you have to be a little bit more careful if you really want to count. But the upshot is that if there are t marked elements, but you don't know that, you might still have to do more than root n over t queries, because you're trying to figure out how big that period actually is. But you're certainly not going to, in the end, have to do much more than square root of n queries. Okay. Now, there are other solutions to this that do let you get more like square root of n over t. But I kind of like this one because it brings in Shor's algorithm again. OK? Yeah?
I don't understand that graph that you're assuming that it's sinusoidal.
Oh, yeah, because I just calculated it, right? So this is the state that I have, exactly the state that I have after k iterations. And so what's the probability of getting a marked element? Well, it's sine squared 2k plus 1 theta. That's all. Any other questions? Yeah.
How does this affect the computational cost?
Right. So you basically, in order to get enough periods that this Fourier transform is telling you something, I mean, it depends on how exactly you want to know t. Right? If you want to know t to really high precision, then you have to do many, many queries. And it turns out, if you want to know t exactly, then you're kind of back at the O of n size. But in order to be good enough to solve Grover's problem and to produce a witness, x0, is still of order square root of n. Any other questions about this? OK. So like I said, Grover's algorithm has a wide variety of applications to basically anything where you kind of try some long list of things. What's maybe not obvious is it has applications in quantum algorithms to speed up some things. Again, it's only a quadratic speed up relative to kind of the naive way of doing it, but sometimes that can still be very useful. And so this variant is called amplitude amplification. And the way it works is this. Suppose we have some unitary which starting on the state all 0 gives us the state 1 minus epsilon times some state psi plus the square root of epsilon times phi. So here, I guess I've normalized. And what we really want is phi. OK? So we'd like to get phi, but all we have available is some unitary that gives a very small overlap with phi. OK? So that's pretty bad. And depending on exactly how this works, you might be able to do some checking. And you can try it. And if it worked, then you keep it. And if it doesn't work, then you try again, and so on and so forth. But then you have to do 1 over epsilon trials. And so amplitude amplification is a way of building up these amplitudes coherently, just like in Grover's algorithm, so that you can get a high amplitude for phi with only doing something you like 1 over square root of epsilon times instead. And yeah, so here I'm assuming that psi is something orthogonal. And the other thing I want to assume here is that we have a measurement that reliably distinguishes phi and psi. Of course, when they're orthogonal, such a measurement always exists in principle, but it might be very complicated in practice. So in order for this to be useful algorithmically, you need one that's efficient in whatever sense you're dealing with now. OK, so the thing is, then, since we have this measurement, we can purify it into some quantum operation using an ancilla, where instead of just measuring the difference between phi and psi, we do some C0 type gate into an ancilla. Right? And the ancilla becomes 0 if the state is psi, and it becomes 1 if the state is phi. And if you think about it, that's exactly what this oracle was doing, just with classical inputs instead of the state psi and phi. Right? If we have the state t, then we get 0. If we have the state s, we get 1. And so if we do a phase shift on this ancilla qubit, a z, then we're getting this minus sign. We can do 2 of these coherent versions of the measurement, which are the oracle equivalents. We do the phase kickback. And so actually, if we're doing it that kind of controlled NOT gate to the plus state, that's what the phase kickback does. We can do it with just one application of the purified measurement. And the upshot is that we're getting a -1 to the O operation. That on the state phi gives us a phase -1, and on the state psi gives us a state +1. OK. And so then we also need, for Grover's algorithm, we also needed this -1 to the u. So what does that look like here? Well, so before we were using the Hadamard. So this state here is kind of the equivalent of our U state from before. And before we're using the Hadamard to transform back and forth between all zeros and the U state. Now we're just using U. Okay? So -1 to the U is basically going to be the same. Let me get the daggers right. So we have U, F0, U dagger. Okay? And so we still have a G operation, which is really the same. It's -1 to the O, -1 to the U. And if we apply, so if we, well, apply G to the U state m times, well, we rotate it just like we had before. And we get roughly phi with high amplitude if m is about 1 over root epsilon, right? I mean, I guess it's sorry, I didn't write down what the constants are going to be, but is it? I think it should be pi over 4, 1 over root epsilon. Okay? And so again, this is a way of getting some particular quantum state, provided certain conditions about how we can create that state. Even though we have some procedure that only gives a small amplitude of it, we can amplify that amplitude and get it up to a large overlap with the state phi. Okay? Any questions on that? Yeah.
Can you explain what the purify measurement is again?
Yeah. So yeah. So here's the simplest version of purifying a measurement. So suppose I have some qubit and I just want to measure it. Okay. This circuit is equivalent to saying, oh, I'm going to take an ancilla here, and I'm going to do a C0 gate, and then I'm going to measure the ancilla, right? Because this started out alpha 0 plus beta 1. So at this point, I have alpha 0, 0 plus beta 1, 1. And so the measurement outcome here will be 0 or 1 with probability alpha squared or beta squared, just like if here. And if we get 0 here, then this collapses to 0. If we get 1 here, this collapses to 1. So this is kind of a non-demolition version of this measurement. Okay? But now, suppose I don't measure this. Well, the state of this qubit up here is just the same as if I had measured this, right? Because I can't tell whether I measured it or not. And I can use this qubit just like I would use a classical qubit. Okay? But I'm doing it in quantum circuitry now. So the fact that I measured it, all the measurement does is it converts it from a qubit into a classical bit. The thing is that this C0 has already decohered this qubit just like a measurement would. And so that's basically what I'm doing over here when I say I want to purify the measurement. So what does it mean when I want to do a measurement in this case? Well, that's a little more complicated because it's not just a 0-1 measurement. It's a phi-psi measurement. But let's not get into the details of how that's done. We have some qubits here. We have something here. And we could do that measurement this way by it's doing some complicated thing up here. And then we have an ancilla down here. Right? And then if I just forget to do this part of the measurement, that now it's purified. Okay? And that's acting the way I want it to. And then if you use this on the state plus instead of the state 1, or sorry, the state minus instead of the state 1, then I get this phase kickback, where instead of entangling with this ancilla, now what I'm doing is I'm putting a phase up here. Does that make sense? OK. Any other questions? Yeah.
Now, usually, how small is epsilon to estimate the?
Well, it very much depends on the application. But most often, you're going to do it in a case where you have an analysis that tells you what epsilon is. And so you do know in that case. But you don't have to. You could be in a situation where you don't know, and then you have to do this approximate counting thing to kind of estimate what it is. It's a similar idea, but. Anything else? OK, so that's it for the lectures on algorithms. You have a tutorial today where you'll wrestle with some of these things some more. There's another kind of, so I've shown you, there's kind of 3 standard quantum algorithms that everyone talks about. One of them is Shor's algorithm, one of them is Grover's algorithm. And the third one, which is in some sense more practically useful, is simulating quantum systems. And so the tutorial is going to kind of give you some introduction to algorithms for simulating quantum systems. In the years since, those are all dating from the 90s, or in the case of simulation, even earlier. In the years since, people have discovered many other algorithms, none that have kind of quite the same practical impact as these 3. Some of them are polynomial speedups, some are exponential speedups. A lot of them are for very weird artificial problems. One that's not weird or artificial is an algorithm for solving linear equations, which I don't have time to talk about. So it's for solving big systems of linear equations. You get an exponential speedup, but you kind of have to change the question of exactly what you're asking for. So that's and that one is. It's a little uncertain to what extent that has real practical applications. But people have certainly made a number of proposals for that one. So that's called the HHL algorithm for Harrow, Hasidim, and Lloyd. And so that's maybe the 4th big quantum algorithm that I would point to. But it's kind of a little beyond the scope of the class. So next week, we're going to talk about other aspects of quantum information. We're going to talk about quantum error correction, quantum cryptography, entanglement, and channel capacity type things. OK?